Here we are going to walk through the basics of how to build a model and use a model. We'll keep everything as simple as possible, use all the defaults, do everything in a way that requires the least amount of new information. We're going to introduce the caret package. This allows you to look at lots of different types of models. So you can go and look at the caret package. I left some links here that you can go look at. There's some introductions online that you can look at. And one of the great things about this caret package is it allows you to use lots of different types of models. So this is a site that lists all of these types of models. One that you'll recognize, random forest. This is related to the isolation forest we've been using. There are other ones that you might have heard of. There are neural network models. There are simple linear regressions. Just lots of models you can use. And for the most part, they can all be used in the same simple way. Of course, over here on this right, it shows you inputs that you may need to tune or to put into the model. So then the specific model has some variations in terms of how the caret package is used, but for the most part, they're set up in the same way. Okay, so we're going to use the same data we've been using. This is company year data with sales growth and ROA. I have changed it a little bit here, which I'll talk about in just a minute. I have ROA for the year subsequent to what we're observing. So 2019 here, I have ROA for the following year. So this would be 2020's ROA, which is the same notice as 2020 here. So we have ROA from the given year, ROA from the subsequent year, and then we have the other variables that we've already used: research and development, profit margin. This is the log of total assets and sales growth. So things you've seen before. The couple of things I did differently is I prepared the data a little bit. This is going back to what we've done previously. I created a new function, clean, which removes or creates missing values. So if it's NA, if it's the calculated missing, and if it's infinite, then I just set it to NA. And then I remove extremes. So if it's greater than the 99th percentile, I set it equal to the 99th percentile. If it's less than the first percentile, I set it equal to the first percentile. This is sort of a lazy but somewhat effective way to remove a bunch of extremes. And with some of these variables, especially, for example, ROA and profit margin, this is really necessary because of these extremes we have. Of course, we've tried other ways. I'm not saying this is the right way. It's just one way to do it. So I create these variables. I do the natural log. For R&D over assets, I remove, if it's missing, remember, because a bunch of our companies don't have, or at least these databases don't report R&D. So then I set it equal to 0. Only kept a certain number of them. Then for each year, I do this cleaning thing, which means each year, if you're in the 99th percentile or first percentile, I change the variable. So I do that to all of these variables that have extremes. And then I even did it for the log of total assets. That wasn't really necessary. And then R&D I did separately because there are no negative values. So I only removed or changed the top extreme and left the zeros all the same. Okay, so this was just a cleanup step that we need to do before we do any of these models. Not necessarily the correct or the only way to do these types of cleaning up, but these steps are necessary for some of these models that we'll use. Not all of them need these cleaning steps to be done, but all of them can. The ones that don't need it, it's probably not going to hurt them too much to clean it up anyway. Okay, so first clean it up. Then for our, we're going to do some random things. Well, just right here, actually. So we're going to use the same seed so you can get the same thing I have here. We've seen this before too, where we take a sample of the data. Here we use it for a different reason. And in these models, what we're doing is all of this, what we're going to be talking about is trying to use models to predict. And that's a little bit different from exploratory models or models that we're using to test hypotheses. That's not what we're doing here. So if we're going to try and predict, what we have to do is let the model learn the structure of the data, and then we want to then use that model to make some predictions. If you try and let it learn on the same data set that you're going to make predictions, then it can always fit that data really well. Then the problem is when you go to move to a different data set, it will perform poorly. So that's one of the reasons we are careful with how we deal with the data. Another reason is in real time, sometimes we want to make predictions, and the only thing we can do is train the data on data we already have. So then when we go to predictions, we want to make sure these models are at least somewhat robust. So standard and necessary practice, of course, some of the things I'm going to talk about here can be done within the caret package, and it has some nice features related to that. I'm going to show you the conceptual ways that are straightforward to think about. If you want to explore how to do it in other ways using all of the features of the caret package, great. I'm just going to exploit a few of those. Okay, so first we need to have what we're going to separate: a training data set and a testing data set. I removed the vowels here and the endings. So TRN is my training data set, TST is my testing data set. So the training data set would be data that we train the model on. As a general rule, the testing data set, we never set or estimate a model on testing data, because then once you estimate a model on testing data, you now have turned it into training data, and it's not really, you can't evaluate the model anymore. So training data, create the model, fine-tune the model, anything that you're dealing with the model here. Testing data, do not create a model, you're just going to use it for prediction. Okay, so we've got two things. When we separate this testing data, it's like this isolated thing that we can never touch again until we're done with tuning the model. So then this first part is what is going to be the training data. There are lots of ways to do to separate training and testing data. In reality, in the data we have, it's limited. We don't have like, oh, here's a bunch of data, and then we can go get more data to go test it. At least for evaluation purposes, of course, when you're doing predictions in real time, you're creating new testing data all the time that you can evaluate your model. But when we're testing models and trying to evaluate them, we just have to use the data that's available to us. Okay, so I'm taking some fraction of the training data set of the full data set, and here I'm doing 60% of the full data set to create this training data set. So look over here, it's 12,136 rows. And then I'm also going to create the testing data set, and I'm going to use anti-join here. There are other ways to do this since we've been using the dplyr and tidyverse framework. We're just going to stick with that. So we take the first data set. Anti-join means take anything that is in this data set but not in the following data set. So take anything from the first data set, anti-join the training data, meaning anything that is in the first data set that is not in the training data, put it into the testing data. So then over here we see we have 6,142 observations in the testing data. So we have the training data and the testing data. Of course, there are other ways to do it. Sometimes you care more about how a model is performing along some other dimension. So one that we encounter a lot is in a time dimension. So maybe we really care about um, how models perform, this year or the last couple of years. So we might use a time dimension to sort of simulate how we might do this in real time. So one of those ways then is to filter, right, create a training data set based on some dimension in the data. So you could do this based on certain companies or certain industries or certain time periods, right? Lots of different ways you could do this. It all depends on the question you're trying to address. Here, let's use the time. So going to use any years before 2020. So in our project data, that would be 2018 and 19. It's about the same in this data. And then anything after that, we're going to move to the testing data. This is the one I've actually run over here. So training data, testing data. Might as well run this so you can see. So notice in the first one, we get training data of almost 11,000 and testing data of 7,000. We run this one and we get the 12,000 and 6,000. So either way, we end up with these data sets. Then for a lot of models, what we need to do is only put in the data set the variables we're going to use for the model. There are other ways to do it, but I think this is a straightforward way. So from the training data set, we're only going to select the ones I want to put in the model. This is next year's ROA, that's the Y variable. Then this year's ROA, profit margin, sales growth. Well, I don't need profit margin twice. Log of total assets and research and development. So run this, then we end up with this training 2 data set. Notice it is the same number of rows, but 2 fewer variables. That's getting rid of the name and the year. Okay, so I've got this data set ready. Notice in this down here, I've got this training 2 data. That is what I'm going to be using. In the caret package, a way to train a model is with the train function. So the train function says take, and it's going to use some defaults here, take some model method. So here is linear, LM is linear model. So use a linear model with this training data to fit a model, and this model is next year's ROA. This is the Y variable. This tilde here indicates that it's a model. So Y variable model followed by X variables, and the dot here says anything else in the data set. So Y is ROA lead 1 followed by anything in the data set here. This model is what we're going to use. You could put individual variables in here too. From other stuff you've done, you should know how a linear model works. We're going to only focus on the prediction part of this, so we're not going to look at the coefficients or anything. Okay, so we'd run this. This takes a little while to run. The more complex models take even longer, and some of the defaults take, especially long. So we might mess around with that later, but for now, I want you to see how this works. This doesn't take too long. Go ahead, run it. This random forest and this is a different version of a forest model, and some of the others that you might see in the package take significantly longer. So this random forest, you might, if you're going to run it, you might hit run and then walk away for half an hour or something. And depending on your computer speed, it may take even longer. Then this XGB tree is a gradient boosted random forest model. So I just want to show you that there are other models you could use, and we'll use them for comparison. So you run all of these. What comes out of this are these outputs here, and we can look and see what happened with those outputs. So the first one, the linear model, it gives us a sort of indication of what this is, right? It ran through the data a few times. In the end, it ends up with a linear model, which is, it's not going to be really different from just running a linear model without the caret package, but I'm trying to keep within the same package. And running through all of that, the sample, what happens in the data in that sample is an R squared. That's how well does it fit the data, or how well does the model fit the data, explains about 39% of the variation in the sample. So that seems, for a lot of these things, that's reasonably good. We can see the same thing with the random forest model, and now it has to go through different columns to try, right? Do you include 2 columns, 3 columns, 5 columns? The final value, it says the best one we could come up with was 2 of those. Well, the R-squareds, notice the R-squared of the top one is 56% or 57% R-squared compared to the 38% or 39% R-squared. This seems like a meaningful improvement. And then the XGB tree, so the XGBoost version has to run through more tuning and parameters. So notice it's trying other things here. In the end, we get to somewhere in the 40 or 50 range. So it turns out with what it can come up with this model, it's somewhere in between the linear model and the random forest model. However, how this works in terms of once we move to prediction, that's a different story, right? So we don't always prefer the best fitting model in the training data because it might overfit going to the testing data. All right, so then there are a couple of other things we might be interested in. We can look at which variables are most important in each of the models, meaning which ones come up the most, which ones have the largest weight. So in the linear model, it's ROA. So the prior year's ROA is the most important predictor. It does most of the heavy lifting, basically, for the model. Log of total assets is next, and then profit margins. So it kind of goes down from there. For the random forest model, the top 2 switch. So and the bottom ones are the same. So total assets is the dominant one. ROA is next. Profit margin, same order. Interestingly, research and development doesn't matter at all in either of these models. Kind of maybe counterintuitive that we think having a lot of R&D might affect future ROA. Well, prior research finds that it takes a while, right? It's years of research and development before it turns into profitability. Last one, it looks like the random forest model, kind of the same structure here. So, and that's to be expected because they're both based on a tree-based model, so that would seem to be normal. All right, so we've done this training, and right now we've just used defaults here to train these models. There are lots of things we can do that we'll talk about later on how to take different approaches to training them. We've then looked at what they have here, so how well in sample do they fit? So in terms of in sample in the training data, the random forest model seems to work best. We don't know after that. So once you have it all trained, you can then take that model, so the parameters and everything that are in there, you can take that and use it to predict on a new set of data. So on the new set of data, it's going to take only the X variables, so the things that are in the dot here, which would be these variables here. It's going to take those and use those and the parameters in the model to predict what the next year's ROA is going to be. So notice there is no training of the data here, or training of the model, and we're not using next year's, like the Y variable we're not using in the prediction data set. It's just predicting based on these X variables. That's important because then when you go to predict something, you don't have to have the thing that you're trying to predict. So how do we do this? Well, we can use the predict function. We take the model that we've estimated, and this is estimated on the training data. We apply it to the testing data. And here I'm predicting, moving it into the testing data. I'm creating a new column called prediction 1, prediction 2, and prediction 3. If we look at how correlated these predictions are, remember they are different models applied to the testing data. Oh, it says we don't know what these are. Okay. We look in here and we see that the correlation, so the first one, the linear model one, is 77% correlated with the random forest one. The random forest one is 90% correlated with the gradient boosted trees. So the two tree models are fairly highly correlated, but they're not perfectly correlated, and they are somewhat different from the linear model. So how can we evaluate this? Well, we could look in the prediction data set and say, how well does our prediction match what actually happened? So there are lots of ways, again, to do this. I'm going to do the most straightforward, easy way to do it. That is, take a linear model. This is, LM is the function for a linear model. The Y variable is the thing we were trying to predict. This is ROA next year, ROA lead 1. And we're going to do a model of ROA lead 1 that is a function of the prediction that we put in. So if we're right, then the coefficient on the prediction should be close to 1, meaning we think whatever we said for the prediction is really close to what the actual outcome is, and we should expect a high fit, and here we'll use R squared. We're going to use the testing data. So remember, we're evaluating in the testing data. We're not really creating a model or tuning a model, we're just evaluating how it fits. So we can run these. And again, there are lots of ways to do this. I think this is just a straightforward way we could think about. So we could look at each of these and see sort of what comes out of it. The first one, this is the linear model. Notice the R squared is 32%. That's not too far off of, or the adjusted R squared or R squared, they're basically the same when you have one variable anyway. So the fit is almost the same as what we had in the training data, so we didn't lose a lot moving to testing data, so reasonably good. The coefficient is not close to 1, meaning we're sort of missing some things here. Same thing in with the random forest model. We can look and see what that did, and notice now we got 56% R squared, again pretty close to what we got on the training data, so sort of comfortable there. And the coefficient is again closer to 1, so it's better than the linear model. If that's meaningfully different or not, I don't know, but at least better, seems to work fairly well. And then the last one, somewhere in the middle, right? So this is the XG boost, coefficient sort of in the middle, and the R squared is sort of in the middle too. Whether linear model's way better, or the random forest is way better than the other two, I don't know, but at least in what we've used to evaluate it here, that makes sense. So a couple things to finalize here. What we're going to do in the next version is work on parallel processing. So if you have multiple cores in your computer, it can run tuning the model in different components. So then sometimes that can speed up processing here. I just want to show you how to do it. If you had a big cluster of machines, that would be another way to do it that might speed things up. Not necessary, and sometimes it won't help, sometimes it will. And then remember, we prepare all the data. We need to separate the data into training and testing. There are multiple ways to do it, but we need to do that. We need to then select only the variables that we're going to use, and then we can train the model. And we train the model only on training data. We can then look at it and see how the training did, and we're going to use that in some of the stuff we do next. And we can see which variables seem to matter the most. That's just a way to sort of see if anything makes sense to us. And then finally, we take what we built with the model and predict based on the separated data set, which we're calling testing data, and then we can evaluate how well it fit on the testing data. All right, so we can mess around with this a little bit here. It's I think, good practice. You could go forward with just this, but next we'll talk about how to fine-tune some of this.